All right, let's go back to working on this problem. Where is everybody? Ah. Why is he already doing overnight shifts at the hospital? It also causes him to miss class. Not the best, not the greatest decision, is it? I'll give you an answer. No, it's not the greatest decision. No, I'm pretty certain. Yep. Okay. You guys are already done with that test, right? I'm trying. Hey. Okay, so we have a proton accelerating through a potential difference. We have a final speed. What's the final, what is the potential difference? What's when we have the mass of a proton? So of course, we're using the conservation of energy. We're going to bring everything but the final kinetic energy over to one side of the equation. Now, remember that the change in potential, the electric potential energy is final minus initial, but we have initial minus final, so that's going to give us the negative of the electric potential. And then we remember that the change in potential energy is Q delta V. So we want to know the potential difference. So first off, let's look at this. One of these terms becomes zero. What is it? Yeah, because you see it says starts from rest. So initial kinetic energy has to be zero. Because its initial velocity is zero, and kinetic energy is 1/2 mv squared. So this means we're going to have negative Q delta V equals the final kinetic energy of the proton. And then we can put in the 1/2 mv squared. And what is Q in this case? Yep. Mass of the proton, final velocity squared, over 2e, or the base charge. So the mass of our proton our velocity and the elementary charge the potential difference that the proton accelerates through so 20,886 volts, or about 20.9 kilovolts. All right, capacitors. So we use capacitors to store energy. So you can have a power source, a battery, which will which based off the power of the battery, will slowly or quickly charge these plates over a given period of time to a maximum charge. And so then the energy, the electric field between those plates is going to be is going to dictate the capacitance. The simplest version of this is a parallel plate capacitor. If you've ever driven by a substation, on the ends of the substation, you ever see like this, like kind of look like ceramic bells just stacked one on top of the other? Those are capacitors. The ceramic is a dielectric, which we'll talk about in a little bit. And so what those would be is what we call capacitors in series, which will make more sense when we start looking at circuits. All right. So the first thing we want to remember is in last chapter, we talked about the electric field between the plates of a parallel plate capacitor, sigma over epsilon zero. Yes. C is capacitance, delta V is change in potential. And again, make sure you're keeping straight potential versus potential energy. Okay. So we also remember our Boltzmann constant, 1 over 4 pi epsilon 0, which means we can solve for epsilon 0, 1 over 4 pi ke. So later on, when we're working with electric field in here, we can remember that so we have a different way we can represent electric field if we need to. before we really go there, let's try to keep this, let's simplify this. So let's say, again, what is sigma? You should by this point. Who knows what sigma is? We have lambda, we have lambda, we have sigma so far. Surface charge. It's charge per unit what? Squared. Oh, you skipped over the one in the middle. Area. Is that what you said? Say it louder. So you remember your lambda is your linear charge density. Your sigma is your surface charge density. So if we know that that's charge per unit area, then we can have Q over epsilon 0A. We also know that voltage or potential is going to be electric field times the distance separating the two plates. We can put in our electric field, so it's going to be UD over epsilon 0A. Do what? Well, your voltage is electric field, your electric field multiplied by the distance, the separation of the two plates. So if we solve this for Q, Q is going to be epsilon 0A over D times your voltage. So this gives us our definition. So our charge is going to be capacitance delta V, where our capacitance is going to be epsilon 0A over D. And if you're solving problems and you need to, you can always go back and plug in the 4 pi K sigma. And solve from there, use that as your electric field. So that would be, so what your E. And then you could solve for Q and get another expression for your capacitance equation. And that Q is going to be the charge. It's the charge on the plates. It doesn't have to be 2Q because remember that each plate is the same magnitude of charge. So there's really a couple of ways to go about this. But it helps to remember that you have these multiple expressions for electric field based off what you're given in a problem that you need to solve. Alrighty. So we have a parallel plate capacitor. Both plates are an area of 1 square centimeter, separated by 0.250 millimeters. So again, that's your D. That's your A. There's a charge magnitude of 4.0. What's PC? Picocoulombs. Yeah, pico is -12. Nano's -9, angstroms is -10. Pico is -12. And so let's find the potential difference in the electric field between the plates. And if the plate separation is doubled while the charge is kept constant, what will happen to the potential difference and to the electric field? Okay. Now we know we can go back to our capacitance equation. So our potential difference is going to be Q over C. And remember that C, oh, we can just go ahead and use epsilon 0 A over D since we have A and D and epsilon 0 is a constant that we can look up. If you were looking that up, what would you look up? Yeah. Well, why don't you tell me what if you were looking this up in your index, what would because you can't look up epsilon 0, you have to know its name. Actually, it's on if you find your tables in your book, it's on there too. You remember what it's called? It's a universal constant. What? P. What'd he just say? Of what? No. Where's the primary place that we would judge electric fields before we started getting dielectrics in place? Like the air in the atmosphere can be a dielectric. Where is the electric field unimpeded? The denser the material, you're going to get more dielectric unless it's a metal, not the ground. Where's the least dense place you can think of? No. Less dense. Yep. That's air. Which is what? Space is a what? Does it have, well, oh no, there's lots of gravity. You just have to learn where it's at. So a long time ago, they thought space was filled with the ether, but it's not. What is it? It's what? It's a nothing, which we call a it's the permittivity of a vacuum. No, look. Every time I give you guys an answer, someone always goes, I said that. The vacuum chamber does suck out the air. When did you say vacuum chamber?
You know that I actually said that still has air. Replay the video back.
All I know is every time I give you guys an answer, someone says, I said that. I'm just not certain I believe it anymore.
I'm gonna find where it says vacuum chamber. That still has air. I'm gonna show it to you tomorrow.
Okay.
What is this vacuum? What do I say vacuum chamber? Maybe I just said vacuum. I was thinking the local stuff had no air because air was vacuum. Okay, listen.
I was probably answering Maggie when she said the atmosphere.
Oh, probably. Maybe you didn't hear my dialogue.
It's possible.
That's the vacuum. That's who said that still has air.
Yeah, because you said air, And Maggie said, atmosphere. Is like, no, that's still air.
But, well, I'll show you the video.
Okay, so if you're looking this up, you're looking at the permittivity in of a vacuum. That's epsilon zero. Okay, so now, like I said, you could go ahead and you could do this in terms of 4 pi k, and just look up your Coulomb's constant if you wanted to. But since we know that we can look epsilon zero up, there's our charge, our distance, millimeters is 10 to the negative third. Permittivity of a vacuum. And then our distance. Where did I get this? No, our area. Sorry. So it's square meters. How do I get that? Because I have 1 square centimeter. How do I convert that? Pretend I don't know. Yeah. Yeah, actually that would work. Yeah, it's 10 because, well, because remember 100 centimeters is a meter, but 10,000 square centimeters is 1 square meter. So if I square it, I take the 100 squared. It'd be a million. So it'd be 10 to the negative 6. So when we calculate this, our delta V, 1.13 joules per coulomb. What is a joule per coulomb? Volts. Now, part B. Do you think you can do that without using any numbers? If the plate separation is doubled while the charge is kept constant, what will happen to the potential difference? So we start here. So how much larger is delta V2 than delta V1? Twice. Yep. So what would happen if I doubled the distance between the plates and made their area half what it is? Yep, quadrupled. Double the distance and half the area. Yeah, so it'd essentially be 2 over 1/2. All right, dielectrics. These are the materials that you use to make your capacitor store more energy. These are going to be insulating materials that you stick between the plates of a capacitor. Does that seem right that I'm going to use an insulating material to increase the energy storage of the capacitor? Does not what? Well, no, it touches. What 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 does an insulating material do to the electric field? Okay. It does what? Yep, it resists the flow, it resists the electric field. So to get that electric field to completely charge the capacitor, you're gonna have to do more what? What is the physical quantity that you use to charge a capacitor? It goes from 0Q to Q. You're moving charge. So you are moving charges. What do you have to do to move charges? No, you're using the capacitor. There's a dielectric now. It's an insulating material. It's resisting the electric field, but it's increasing the amount of energy stored in the capacitor. What does the battery do to move charges? It's in a circuit. To move a charge, you have to apply a force to it. Okay, so you apply a force to the charge. When you move a charge, does it go across a distance? So it's a force applied across the distance. Gives you newtons times meters or joules. The newton meter, that's a joule. What physical quantity is work done across a distance? Oh, it's work. God damn it. We'll just. Yeah. So you have to increase the work done to get the electric field across the capacitor. And resisting that electric field, you're actually going to increase the energy stored in the capacitor due to the work needed to charge the capacitor. Okay. So what you're seeing, the only difference to what we've been doing is the capacitor you were looking at that we just looked at had no dielectric material. So your capacitance was epsilon 0 A over D. Now it's kappa epsilon 0 A over D. So the kappa is your dielectric constant. Yeah. Lowercase. But your dielectric constant will be unique to your material, which means if you have to use it in a problem, you'll do what? How do you figure it out? Yep, you're gonna have to look it up. Every dielectric material has its own individual dielectric constant. So you'll just look that up and you'll use it. So your capacitance will be increased by a factor of your dielectric constant. And so your dielectric constant is E0 over E. So E0 is the electric field in a vacuum, and E is the electric field in the capacitor with the dielectric in it. Okay. Parallel plate capacitor has plates of area of 1 square meter, spacing 0.5 millimeters. Again, that's your D, that's your A. The insulator placed in there has a dielectric constant of 9.8. So that's our kappa. And dielectric strength of 9.0 kilovolts per millimeter. Nope, that's not your, nope. That's actually your E, your dielectric strength. That's your dielectric constant. See, what is the capacitance? What is the maximum charge that can be stored on this capacitor? So and you're going to want to look that up in the textbook. The dielectric strength has a specific definition. It's the electric field, the strength of the electric field at which point the dielectric breaks down and becomes a conductor. Yeah, so you'll see where we use it. We use it for part B. So again, dielectric strength, dielectric constant are going to be unique to the material you use. If you're ever building a circuit and you use a material where the dielectric strength is not large enough, and that material breaks down, you will short circuit your whole system and the entire thing will fry. So you want to make sure you know these things. Circuits. Yeah, but we had this fun little system. It's kind of like circuitry by Minecraft. Very much so. That'll be when we're working on circuit diagrams. And then, of course, last year, everyone hated Kirchhoff's rules, but I think they make circuits a lot easier. But we want to know, let's see, what is the capacitance? But hang on. Give me a second. Okay, so how do we get there? Okay. So okay. So we can go there. Our epsilon 0 No, not equals, times, kappa times. Okay. Just another way to solve it. So our kappa is 9.8. Let's see. 4 pi, you can look up what's KE. Yeah, that's your Coulomb constant. Yeah, so it's just another way to solve it. It is. Alrighty. So our capacitance is going to be 1.73 10 to the negative 7th Coulomb squared over newtons times meters. What can we reduce that down to? Coulomb squared over joules. Coulombs per volt. What are we working towards? Yeah, what's the unit we're working towards? Coulomb per volt. Do you know what it is? It's farads. So that gets us our capacitance. What is the maximum charge that can be stored on the capacitor? Well, so what we have is Q equals C delta V. Well, what does delta V equal? Well, that's true. Let's try a different one that actually allows us to use our strength, the dielectric strength, ED. So what? That'll be our 1.73. 10 to the negative 7th. Let's use coulombs per volt this time so it helps make things easier. And then our electric strength, 9.0. Let's see. Let's do something first so we can make the units easier on ourselves. Let's go ahead and do E times D. You'll see why we went ahead and did this. Kilovolts per millimeter. Yeah, millimeters. So separation of millimeters, that's going to give us 4.5 kilovolts. The reason we went ahead and did that is now we can just multiply by 4.5, 10 to the third volts. Otherwise, we would have been fishing around to get all those units the same. Coulombs. So you can go ahead and just plug in E times D there, but you're going to have to get all the units the same. You're going to have to change it to volts per millimeter because then you have a D of millimeters. Or you can just do E times D, get the kilovolts and change it to volts and make it easier on yourself. To volts per millimeter. Because remember, per millimeter, because remember your D is already in millimeters. Well, if you change it to volts per meter, then you'd have to change your D to meters. Yeah. Yep. Energy stored in a capacitor. So of course, again, here's your theorem. When you're solving problems, you can't go straight to the theorem. Okay, so if we think about as we're charging the capacitor, if we think of the capacitor charging by tiny little increments of Q, so you know that our potential energy is Q delta V, and essentially delta V stays constant. So the equation we'll have to solve next time, a tiny change in the potential energy and then the way we solve this is we're going to say that delta V is Q over C. Yeah, that's equivalent to. So it's not just, it's not like an equal sign. This is, it's a logic symbol that means it absolutely means this. It's a definition. Yeah, yeah.